The consensus problem involves designing control strategies to ensure that all agents in a network agree on a common state. This state can be predefined in what we call leader-follower consensus, or it can emerge from the system dynamic itself. In this case, it's called leaderless consensus. A standard controller that guarantees a global asymptotic solution is the following proportional plus damping injection scheme, which includes a term proportional to the position error between the agents, an energy dissipation term, and the inclusion of the gravity vector, which main drawback is that it relies on the exact knowledge of the agent's physical parameters, which are in general uncertain. This work proposes an adaptive PID controller that solves this problem by estimating these unknown parameters. This means that the gravity cancellation term is replaced by a gravity compensation element, where theta is an estimation of the agent's real parameters and is defined by a dynamic estimation law. Also, this controller introduces a dynamic disturbance rejection term that can deal with unknown constant disturbances. Moreover, it is possible to include a component with high gain close to the origin. This term is beneficial for dealing with friction in practical scenarios. Now, we present a comparison between these controllers. We tested the gain parameter uncertainty and external constant disturbances. As a measure of performance, we use the norm of the consensus error, which can be interpreted as the union of the position error of all agents. The network that we use is composed of 3 Kinova rows with 6 degrees of freedom. We experiment with the leaderless consensus problem and with the leader-follower consensus problem, in which we add a virtual leader with a desired position that all the agents must reach. We start with the standard P plus D controller for the leaderless consensus. Here, we see that the agents present error in some joints, which might be caused by friction or parameter uncertainty. Now, we are seeing the performance of our adaptive PID controller, where it is easy to see how the controller is constantly adjusting its parameters to deal with the error. Next, we test the leader-follower consensus. As seen in the graph below, the agents cannot successfully reach the position of the leader, marked by the dashed line. On the other hand, when we test our adaptive controller, all agents manage to effectively reach the position of the leader. Then, we repeat the same experiments, but we add by software a constant disturbance in each joint of the agents. We start with the leaderless consensus case, and, as it was expected, this controller is not able to deal with these disturbances, and the steady-state error is even higher. However, the disturbance rejection term of our controller is enough to deal with this kind of disturbances. Last, we add a constant disturbance to the leader-follower case. Here, we see that the P plus D controller is not able to converge to the position of the leader. Indeed, there is a considerably large error in every joint. But that was not the case for the PID controller. As observed, it was able to solve the leader-follower consensus even with external disturbances.